Welcome to Lyons Township High School AP Physics. Today I've got an example. We're going to do or look at a projectile launched horizontally off of a building. I picked Willis Tower. It turns out that Willis Tower is about 440 meters tall. So we're going to chuck a textbook off of there and see what happens to it. So here's the data for us. We have Willis Tower. Okay, we're standing up there in Willis Tower. The total height is 440 meters, and there's the ground. Okay, and we're going to chuck a textbook with one of those water balloon launchers, such that it's fired horizontally. Okay, and it's going to strike the ground somewhere over here. We're going to launch the textbook at 50 meters per second, which is a little over 100 miles an hour, so it's a good launch. And we're going to figure out several things about the path of the textbook, okay? So first of all, we're going to figure out how long it's in the air. We're going to figure out where it lands along the ground, so that's delta x, a horizontal distance. We're going to figure out its impact velocity, how fast and in what direction is it going when it strikes the ground. Hopefully you know it's more than 50 meters per second because it starts off at that speed and it's going to speed up as it goes down. Also note that it will never go vertically. Assuming there's no air resistance, in this problem we're going to make the assumption there's no air resistance, then it will never be going straight down. It'll always have a horizontal component of velocity to it. After we determine the time in the air and where it lands and the impact velocity, we're also going to sketch the velocity vectors as a function of time and the acceleration vectors as a function of time. Okay, so first off, we are going to figure out the time in the air. Okay, so what I'm going to suggest we do is we're going to split our motion into horizontal and vertical motion. They are independent of each other. They do not affect each other, and you don't mix and match vertical stuff with horizontal stuff. The only exception, the only thing that's the same for both the vertical motion and the horizontal motion is the time in the air. If it's moving horizontally for 3 seconds, it's falling for 3 seconds as well. So I'm going to make a chart. I'll do that here. And we're going to have X and Y, horizontal and vertical. And the most important thing that you can do in a problem like this is write down all the givens that you've got in both the horizontal and vertical direction. Well, we're launching it horizontal, so Vx is going to be 50 meters per second. There is no horizontal acceleration because gravity points down, not left or right. So A is 0. So you notice over here, I didn't put V start or V naught or VI. I just put Vx because it's not going to change. It's not going to change because there is no acceleration in the x direction. Okay? In the vertical direction, what's the starting vertical velocity? When you release the book horizontal, what's its starting vertical velocity? Well, at that point, it's not moving vertically yet, so Vy naught is 0. Okay? As it falls, it's going to pick up vertical speed, but at the moment of release, it ain't going down yet. So it's got a 0 vertical velocity. It's accelerating downward at 9.8, gravity. So we'll call that negative 9.8 meters per second, which brings me to another very important point. You need to decide which direction is positive in your problem. Now, we're going to do both a horizontal and vertical. For the horizontal, I'll say right is positive, and for the vertical, I'll say up is positive. Gravity is directed downward, which is in the negative direction in this coordinate system that I have picked. Now, you may decide to make down positive. That is absolutely fine. If you do that, you would then call this positive 9.8, and again, that's perfectly fine. As a matter of fact, I'll discuss how our problem would change if you did that, and it's very simple, okay? All right, what else do I know? Well, I know how far the book falls, right? It falls 440 meters vertically before it hits the ground. So delta y is, now here's the again, if we're saying up is positive, you got to make delta y, it's going down 440 meters, you got to make delta y negative 440 meters. Okay, so how do we find time? Well, you have different equations of motion. Turns out you've got one equation where if you know v naught, acceleration, and delta y, you can solve for time. That equation is delta y equals vy naught t plus 1/2 a t squared. Now, lucky for us, this term is 0, vy naught 0, so we're not going to have to use the quadratic formula or anything. We will go ahead and solve this for time before we plug numbers in. So if I put 2 on this side and divide by a, and then square root, you get t equals the square root of 2 times delta y over a. And we got all those values, so we can plug and chug. So t equals the square root of 2, delta y is 440, and it's negative. And a is negative 9.8. Now, you've got a negative in both the numerator and denominator, which will cancel out, which they better cancel out because you can't have a negative in the radical. If you did, you'd get an imaginary time, and we're not there yet, okay? So if you plug those numbers in, you should get a time of 9.48 seconds. Now, by the way, I'll make a note. What if we had said down was positive? Okay? Well, if we said down was positive, then delta y would be positive 440, and gravity would be positive 9.8. So you would just make these both positive, and they'd both be positive there, and your time would be the exact same value anyway. So it doesn't matter as long as you're consistent. Once you pick a direction for positive, double check that your givens actually make sense for that direction, okay? Be very careful on that. That's probably the most important step, writing out the givens and really thinking about the sign, okay? Now, once we've got time, we can find where the book lands horizontally. For this one, we're going to use the same equation we just did. Delta x equals vx naught t plus 1/2 a t squared. Well, in the x direction, there is no acceleration. This term is a goner. So it's really simple. And vx naught, well, it doesn't change. It's just vx. So we have delta x equals vxt, and we got our numbers. Delta x equals 50 times our 9.48 from, the 9.48 from the previous step. That's the only thing these two columns have in common. Okay, and if you multiply those out, you get approximately 474 meters. So that book gets pretty far. It's over a quarter mile. Okay, that's a good throw. All right, now, what about the impact velocity? Well, at this moment, when it's striking the ground, we need to know how fast it's going horizontally and how fast it's going vertically. Well, one of those two you already know. The horizontal velocity never changes because there's no acceleration in the horizontal direction. So Vx is going to be 50 meters per second. We do need to find Vy. So because we have time, it makes the problem really easy. The easiest way to do that would be to say Vy final equals Vy naught plus AT. Vy naught is 0. So Vy final equals negative 9.8 times our time of 9.48 seconds. And you get a Vy final of negative, I got 92.9 when I did this in my calculator, meters per second. Now, quick note, there's a lot of other ways you could have found that velocity too. You could have done the following. You could have said V final squared equals V naught squared plus 2a delta y. You know this is negative 440. You know this is negative 9.8. You know that's 0. You could have found this. Now, the one issue, though, is you'll get V squared equals some number, about 8,400 or so, 8,300, something like that. When you square root, if I said, hey, what's the square root of 4? Well, you got two options. It could be plus 2 or it could be minus 2. And you have to make a decision. The calculator won't do that for you. In this case, you would have picked the minus because you know that when that book is striking the ground, it's moving downward, which is negative in our coordinate system. So that's a decision that you have to make. Now, we've got Vx and Vy, so we can write those out. So Vx is 50, Vy is 92.9. The total impact velocity will be the Pythag of those. If you do Pythagorean's theorem and 50 and 92.9, you would get about, it says 106 according to my calculator, meters per second at, you want this angle, the one where the picture started, okay? And if you can do inverse tangent of 92.9 over 50, that would give you an angle of 62 degrees, approximately. And how would you say that? A misconception would be to say, 62 degrees south of east. Is that what we're talking about here? We're talking about east and south? Nope. We're talking about downward. This thing is going downward from the horizontal, okay? So you can say 62 degrees below horizontal, okay? That's the impact velocity. It's 106 meters per second at 62 degrees below the horizontal, okay? Finally, I said we're going to sketch the velocity vectors and the acceleration vectors for the path. So what I'm going to do is I'll go ahead and sketch the acceleration vectors on here. And we'll say it's in the air for almost 10 seconds, so we'll do like 2-second intervals. So split up into about 5 segments. So, 1 and 2 and 3 and 4 and 5. And it's not quite right. Actually, a 5th one should be down here, but we'll go with it. All right, what's the acceleration after 2 seconds? Well, it should be a real easy one. What's the acceleration the whole darn time this thing is in the air? The acceleration is always the same. It's always gravity. It's always down at 9.8 meters per second per second. So if I'm sketching the acceleration vectors, this is going to be 9.8, this is going to be 9.8, this is going to be 9.8, this is going to be 9.8. They're all going to be the same length, etc., etc. They're always 9.8. They're always meters per second, or meters per second squared. So sketching acceleration of a projectile is really simple. It's always down. It's always 9.8. Okay. What about the velocity vectors? Okay, so I'll sketch those on a different sketch. Okay, so our book is released here. It's hitting at some angle. Again, we'll do 2-second intervals. So here's 0, here's 2 seconds, here's 4 seconds, here's 6 seconds, here's 8 seconds, and then an impact, which is like 9.48 seconds, right? All right, when you first let it go, its horizontal velocity, Vx, is 50. Its Vy is 0 because you're releasing it horizontally. How about after 2 seconds? Well, the Vx is never going to change. There's no horizontal velocity. So this is always going to be 50, and I'll just write the number in, 50. And those arrows will stay the same, 50 and 50. On the other hand, Vy is going to change. This book is accelerating downward. We can use Vy final equals Vy naught plus At. And Vy naught is 0, okay? So all we're going to do is at each 2-second interval, so that's 0 seconds, 2 seconds, 4 seconds, etc., we're just going to take 9.8, that's the downward acceleration, times the time. So for the first one, if you do 9.8 times 2, you get 19.6. Now notice, I'm drawing that arrow smaller than this arrow because 19.6 is smaller than 50. If I do 9.8 times 4 seconds, you get 39.2. So that's almost the same size as this arrow. If you do 9.8 times 6 seconds, you get 58.8. So now this arrow is going to be a little bit longer than the horizontal one. And at 8 seconds, you would get 78.4. So that arrow is significantly longer now, and so on. So basically, your vertical velocity is increasing. Each arrow is getting longer as you go. The horizontal arrows, they don't change a bit. So that's an example of a projectile launched horizontally and determining basically everything you'd want to know about the path of that projectile. I hope that was helpful. Thank you very much.